So you guys have already finished this chapter, right?
Yeah.
Okay. So here in fluid mechanics, the main concepts are basically couple of things. There is continuity of flow, fluid flow, and Bernoulli's theorem. These are the main things. But before that, we need to understand things like pressure in a fluid and Pascal's law. Pressure in a fluid and Pascal's law. So we'll be able to characterize fluids on the basis of how it reacts to pressure. So basically, what we will learn is that a fluid cannot sustain any tangential stress. So what does that mean? That means if there is a fluid like this, you cannot have any tangential stress like this on the surface of the fluid, because as soon as you have tangential stress, it will move, the fluid column will move. Okay, to relieve that stress. You can have pressure in this direction, you can have pressure down like this, right? But you cannot have pressure in this direction, a force in this direction, because fluids are called fluids basically only because they can flow, right? Flow means their layers of fluid can move across each other, right?
Right.
Yeah.
Yeah.
So basically we'll be studying different types of fluids and understanding pressure and multiple other properties of them. So first thing that we'll look at is pressure in a fluid, and pressure in a fluid depends on the weight of the fluid column above it. Okay, so if you take a cross section area, right, cross section area in a fluid, pressure at certain depth, let's say like this it is, and what we want to calculate is pressure at this level. Okay, and suppose this fluid is exposed to the atmosphere here, so you have atmospheric pressure from the top, right?
Yeah.
Yeah.
ATM. So atmospheric pressure means pressure is forced by area. So if you take the area of this as del S or something, then force on the top is P into del S, P ATM into del S,
Yeah.
P ATM into del S. And we are drawing the free body diagram of this column of fluid. Okay. So what we have is there will be weight also. This column will be facing a downward weight, right?
Yeah.
Yeah.
So that will be, say, let's say weight W, which can be written as rho, which is the density multiplied by height of the column
Right.
into area of the column. Area into height will be the volume. So volume multiplied by density will be mass and multiplied by G, right?
Yeah.
So this is the force that is downward, plus there is an atmospheric pressure force here. And
Yeah.
if it is in equilibrium, then there must be a down pressure here, right? Then
Yeah.
Yeah.
if it is in equilibrium, then P del S must be equal to P ATM del S plus rho del S Hg, right? So you'll get P will be equal to P ATM plus rho GH plus rho GH, right? So as you go down, the pressure keeps increasing. Pressure here is PATM, and as you go down, it is PATM plus rho GH. Rho is the density of the fluid that we are discussing, right?
Yeah.
So this is straightforward only. Sometimes what happens is there are situations where there is accelerating fluid column, right? You can have a container of fluid that is moving this side with acceleration A, right? Now, what will happen in this situation is that if you take a horizontal column of fluid, right?
Yeah.
So pressure here will be like this, and pressure here will be like this, right? Let's say this is P1, this is P2, correct?
Yeah.
And weight is vertical. So weight does not influence it in the horizontal direction, right?
Yeah.
So what you have is basically P2 minus P1 into del S, right? Is the net force in this direction, right?
Yeah.
P2 del S minus P1 del S is net force in the horizontal direction should be equal to mass into acceleration, right?
Yeah, yeah.
Yeah.
So rho A del S is the mass into acceleration A, right? Correct.
Oh, yeah.
Wait, rho A del S is wrong. Del S into H or length, right? Length of this
Oh,
column is L.
yeah.
So del S into L, this is the mass multiplied by A, right?
A.
Del
Yeah.
S can cancel here and you get basically P2 minus P1 is equal to rho AL. P2 becomes equal to P1 plus rho AL, right?
Yeah.
Yeah.
Now, this tells us that pressure at this point is higher than pressure at this point, right? So that generally is not likely if you are at the same fluid level, right?
Yeah.
If you
Yeah.
are at the same fluid level, then pressure should be the same because you are facing vertical force like this, right?
Yeah.
Pressure at that level is due to this, right? And pressure at
Yeah.
this
Yeah.
level is due to this, just like we did earlier, right?
Yeah.
So
Yeah.
if there is a difference in pressure here, that means there is a difference in fluid column length also, right?
Yeah.
Correct.
Yeah.
So basically what you should have is P1 is equal to P ATM plus rho G H1, right? This is H1, let's say, right? And
Yeah.
P2 should be equal to P ATM plus rho G H2, right?
Yeah.
That should also be true, no? Because if
Yeah.
you
Yeah.
take a vertical column, this should happen, right?
Yeah.
Yeah.
So now because we have one relation connecting P2 and P1 here, we can do another difference here. So we can say P2 minus P1. P2 minus P1 here will be rho G H2 minus H1, right?
Yeah.
That must be equal to rho AL, right?
Right. Yeah.
Correct.
Yeah.
So since both these things are equal, what we get is H2 minus H1 is equal to rho will get cancelled A by G into L, right?
Yeah.
So basically
Yeah.
that tells us that in this case, H2 is higher than H1, right?
Yeah.
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 Right.
Fluid column will be like this, something like this. H2 must be higher than H1. And also we know H2 minus H1 by L is equal to A by G, right?
Yeah.
Yeah.
So if you construct a triangle like this, uh, if this height is H2 minus H1, extra height, right? This is H2, this is H1, so this much is H2 minus H1, right?
Yeah. Yeah.
H2
Yeah.
minus H1
Yeah.
by L is the length here. That looks like tan theta, right? That
Yeah.
looks like
Yeah.
tan theta, the slope of the fluid curve, fluid surface, right?
Yeah.
Yeah.
So you get tan theta is equal to A by G. Okay, so in this case, the fluid surface will be like this, correct?
Yeah.
Yeah.
So these types of things you should learn how to do. Basically, take free body diagrams of columns of fluid and basically understand how they must be. What are the forces acting on them and what is the equilibrium situation. So that gives you an idea of the fluid level, the depth that you are considering and so on. Correct?
Yeah.
Yeah.
Now, the same situation could have been repeated in a slightly different way if it was a rotating fluid, right? Rotating box or something in which there was a fluid, right?
Yeah. Yeah.
You could have an axis like this and there is an omega rotation, suppose, right? So again, if you take a fluid column here, you will realize that there must be a centripetal acceleration, right?
Yeah.
Yeah.
Centripetal acceleration, if pressure here is higher, P2 is higher than P1, right?
Yeah.
Then only it is accelerated towards the center, right?
Yeah.
And P2 is higher than P1 means this level is higher, right?
Yeah. Yeah.
And in a rotating fluid column, this side also it will be same, right? It will be something like this, correct? You can find a relation between this height and this omega and all. It will come something like P2 minus P1 is equal to half rho omega square r or something. I don't remember, but it will come in the same exact way, right?
Yeah.
What,
Yeah.
what will you do? You'll do P2 minus P1 into del S should be equal to M, whatever is the M, R omega square, right? M
Yeah.
L
Yeah.
L omega square, correct? And
Mm.
similarly, you'll do P2 minus P1 should also be equal to H2 minus H1 rho GH, right?
Yeah. Yeah.
H2 minus H1 GH, G rho, right? Del S, right? Should be equal to del M L omega square. And del M is rho A, rho del S into the length, right? So length of this column is L only. No, that will not be L. Length of this column will be something. Length of the column will be L, but the this omega square R will be something else, no? Because R is constantly changing, right?
Right. Yeah.
Right. So
Yeah.
acceleration is not one constant thing. So you have to actually integrate here. Okay.
Mm.
So you cannot do it directly like this because acceleration is varying with distance, no?
Yeah.
Yeah.
Right. So you'll have to take a small element. Take a small element at a distance r, dr, and so on, and take the pressure at this moment, right?
Mm. Yeah.
You understand? This equation is not correct because here I have assumed one constant thing, right?
Mhm.
Constant
Yeah. Yeah.
acceleration towards the center, that is wrong. So you have to actually integrate it and get the pressure variation. Okay.
Yeah.
So you can try that later. This is a standard question that is there in any book. You will find an example. Probably in your Allen book also this will be there. Half omega r square or something will come. Okay. So you should look through this and try it yourself. I'm just giving you examples of how the fluid surface will be in different situations, and it is just free body diagrams that you are drawing. Okay.
Yeah. Yeah.
Then we come to Pascal's law. Pascal's law is very simple. It says that if any external pressure is applied to a liquid, that pressure is transmitted to all parts of the liquid instantaneously. To a liquid, the pressure is transmitted to all parts of that liquid. So even if you apply a pressure at one end, the other end will also feel that pressure.
Right.
All parts of the liquid. So this is the principle by which you have hydraulic lifts and all. So what happens is you take a narrow column here and a wide column here.
Mm.
Wide column here, and let's say we fill it up with fluid, right?
Right.
Now there is a piston here that can be pushed by some P, right?
Mm.
So there's an applied pressure like this P. By Pascal's law, that P pressure is transmitted here also.
Yeah.
P pressure is transmitted here also, and here also there is a piston, and now this P pressure is acting here. Now in this section, you are doing force of P into del S1, right?
Yeah.
Yeah.
Because pressure into this area is del S1, and here it is del S2, right?
Yeah.
So
Yeah.
the force that you get here will be P into del S2, right?
Yeah.
So you can apply a force of 100 Newton and get a force of 100,000 Newton if your del S2 by del S1 is 1000, right?
Yeah. Yeah.
Correct.
Yeah.
Because pressure is transmitted equally everywhere, but the area is in a ratio, right?
Yeah. Yeah.
So you will be able to exert a force here and lift a truck. It is possible, right? If you
Yeah.
design a machine like this, you can put a force here, and on the bigger column side, you can put a heavy weight and that can be lifted, right?
Yeah.
Which would not have been possible otherwise by yourself, right?
Yeah.
However, it is not like this is not violating energy conservation. Not violating energy conservation. It's not like you've gained anything in terms of energy here. It's not like this is providing any energy or anything, because the work done by your force here, right, will be this into displacement, right? So let's
Yeah.
say you displace it by del x1, right?
Yeah.
The work done here would be P del S into del S x1, right?
Yeah.
Yeah. Yeah.
Force into del x1. What will happen is work done is the same here. So if you displace it by 1 meter here, then you will get only a 1 mm displacement up.
Mm.
Like the force is magnified, but the displacement is much smaller.
Yeah.
Yeah. Okay.
Yeah.
So work done is still the same. So whatever work you do, that is what your output you're getting. It's just that the force has been magnified, so you're able to lift it, which you would not have been able to directly. But obviously, you will have to push much farther here, and you'll get a very little raise here, right?
Yeah. Yeah.
Ah. Yeah.
So it doesn't violate energy conservation or anything. That is Pascal's law. Okay. Then if you look at the book, there is section 13.4. He's talking about atmospheric pressure and barometer. So barometer measures atmospheric pressure by measuring the height of a fluid column, right? So
Yeah.
what they do is take a fluid like this and put a capillary tube or something here, right?
Mm-hmm.
Now, because atmospheric pressure is acting like this, there is atmospheric pressure like this also here, right?
Yeah.
That pressure is transmitted everywhere, right? So
Yeah.
fluid will rise in this column as a result of this pressure. Okay.
Mm.
So fluid rises in this capillary, and the amount that it rises depends on the atmospheric pressure, because this force is P ATM into S, and the downward force is weight of the fluid column, right?
Yeah.
So rho G area S into H, right?
Yeah. Yeah.
So those forces must be balanced in equilibrium. So you have P ATM is becoming rho GH, right? So now you can measure pressure of the atmosphere directly by measuring the height of the fluid column here.
Yeah.
So if the height of the fluid column is big, then there is a high pressure in the environment, right?
Mm. Yeah.
So that is what is happening here. That is why we use mercury thermometers, because mercury as a liquid in these barometers also sometimes, because what happens is mercury has a high density,
Density.
13.6 gram per centimeter cube, whereas water is only 1, right?
Yeah.
So if you are using mercury, the height raised is not so much as compared to water, right?
Yeah. Yeah.
So that's why we say 760 mm of mercury.
Yeah.
The height of the atmospheric pressure is enough to raise mercury to 76 centimeter height,
Mm.
almost a meter, right?
Yeah.
I mean, 3/4 of a meter, right?
Yeah.
If you were using water, you would have to take 13 times that, right?
Yeah.
Some
Yeah.
8-9 meters high column you will need, right?
Mm.
So that will not be convenient. So that's
Yeah.
why mercury barometers are used, because the rho is high, so you will be able to measure it easily, right?
Yeah. Yeah.
Okay. Okay. Then you should read about this manometer, barometer, how it is measuring things. Very
Mhm.
straightforward stuff. If you are able to draw the free body diagrams, and remember that pressure at the same level in a fluid should be same,
Yeah.
right? So unless there is some acceleration and all, pressure at any 2 points which are at the same level will be same, right?
Yeah. Yeah.
Inside a fluid. So the only exceptions are cases when we already saw the accelerating case, right?
Yes. Yeah.
Then we have Archimedes principle. Archimedes principle, everyone knows. Basically, what is the principle? Can you tell?
So the buoyant force is equal to the weight of the water displaced.
Uh, so whenever something is in water or a fluid, the buoyant force acts on it in an upward direction. This buoyant force is equal to weight of the fluid displaced.
Yeah.
Weight is equal to weight of the fluid displaced. Fluid displaced. Now, now this buoyant force is actually nothing but an a statement of, or Archimedes principle actually is nothing but a statement of the pressure variation. Okay, so
Mm.
we already saw pressure variation. So now let's try to understand what is going on here. So suppose something is floating like this. right? Something is floating like this, completely submerged, right?
Yeah.
Yeah.
So let's say this is a cube, A, everything is A. Okay?
Yeah.
This is a cube, and density of water is rho W, density of solid is rho S, right? Now let's do the free body diagram of this. So upward, it is facing P ATM into A square, right?
Yeah.
Yeah. Yeah.
Upward surface, it is facing this much force. Downward surface, we don't know what is the force right now. It will be P1 into A square, right?
Mm-hmm.
And its density is rho S into A cube into G, this weight force, right?
Yeah.
So if it is floating, these forces must be balanced, right?
Right.
If it is floating, all three forces must balance, correct?
Yeah.
So P ATM into A square plus rho S into A cube into G should be equal to P1 into A square, right?
Yeah.
Correct. So now see, what you can say is A square cancels, and this is AG, right?
Yeah.
So you're getting the equation P1 is equal to PATM plus rho AG, right? Rho solid AG,
Yeah.
correct?
Yeah.
Correct. Rho solid we are getting, which is slightly weird, but fine. Correct. And okay, P1 is coming like this, and P1 would have also been equal to PATM plus rho liquid, rho water AG, right?
Yeah. Yeah.
That doesn't seem right. Something is wrong. 1 second. Are we missing some force or something? PATM into A square, P1 into A square. See, the difference between this and this is called buoyancy, okay? So
Mm-hmm.
P1 into A square minus PATM into A square is
Mhm.
called the force of buoyancy.
Okay. Yeah.
The lower pressure is pushing it up, upper pressure is pushing it down. That difference will be P1 minus PATM should be P water AG, right? Into
Yeah.
A square. That is the force of buoyancy. So because P1 minus PATM will be what? P1, this equation should be correct, no?
Yeah.
Because you were at a depth A. This is P1 and this is PATM.
Yeah. Yeah.
So this equation, weight of fluid displaced. Why is it weight of fluid displaced? Because it is, see, density of water into volume of the cube, right?
Yeah. Yeah.
In this will be the mass of the fluid if it was fluid here, right?
Yeah. Yeah.
So this is weight of fluid displaced, and that is equal to the force of buoyancy. So force of buoyancy is just a different name for the difference in pressures which causes a upward force, right?
Yeah.
So
Yeah.
I'm just confused over why we are getting this equation. 1 second. Rho S PATM into A square downward, rho S into AQ into G downward. Oh, okay. I understand now. So this is implying, we had assumed that it is floating, no, here.
Mm-hmm.
This is implying that it will float only if PW is PS, right? Which is
Yeah.
true,
Oh, yeah. Yeah.
right? This means just that it is floating only if it has same density, right?
Yeah. Yeah.
It will float with like this, with completely submerged floating will happen only if PS is equal to PW, right? These two equations imply that only.
Yeah. Yeah.
You understand?
Yeah.
Otherwise, it would have floated with a different ratio or something. If
Ratio.
PS,
Yeah.
it could have been like this also, right? Then PS is less than PW.
Yeah. Yeah.
Mm-hmm.
Okay. Or it could have been other situations also, correct?
Yeah.
Yeah.
Or it could have been sinking, then PS is greater than PW, right?
Yeah.
So basically what I want you to understand is that force of buoyancy is nothing but the difference in pressures between the lower surface and upper surface, which results in an upward net force, right?
Yeah, yeah.
That upward net force is called buoyancy. So this part, P1 into a square minus PATM into a square for this particular case.
Yeah.
And once you multiply it by a square and all, you can realize that it will be equal to the weight of the fluid displaced, rho W into a cube into G, right?
Yeah.
So,
Yeah.
so buoyancy can help us basically figure out the densities. If you know buoyancy principle, then you will be able to figure out the densities of many materials as long as you can measure what fraction of it is above, right?
Yeah.
Suppose this is H minus X, right? Correct. This is a cylinder and it is floating like this. Let's say it's a cylinder like this, right?
Yeah.
It is floating like this. I don't know the density of this material. I know water density is PW, right? Now I will be able to predict what is the density of this material as long as I can measure X and H minus X. Okay.
Yeah. Yeah.
Because what I will say, it is floating. So force of buoyancy upward should be equal to weight, right? Weight of the whole thing, right?
Yeah. Yeah.
And the only two forces are force of buoyancy and weight.
Wait. Yeah.
See, now we are not doing three forces. Actually, the forces are pressure, right? And weight and
Yeah.
weight.
Yeah.
But we are calling the difference of pressures as the force of buoyancy, right? So in this case, we can just work with an upward buoyancy force and a downward weight. We don't need to do the actual stuff, which is P1 into this and P2 into this, right? So this is just a simplification of in calling the difference in pressures as the buoyancy, right? So so force of buoyancy is weight. So force of buoyancy will depend on weight of fluid displaced, which is due to H minus X height, right?
Yeah. Yeah.
Rho water into area of cross section into H minus X, right? Into G.
Yeah. Yeah.
Is equal to weight of the solid, which is rho solid into H into S into G,
Yeah.
right? So you get SS and GG cancels and you get rho solid is equal to rho water into H minus X by H,
Yeah.
right? So rho solid is some fraction of density of water. That's why it is floating, right?
Yeah.
So basically it is rho W into 1 minus X by H, right? That is the density of the solid here, correct? So you will be able to measure things like this because of this Archimedes principle. Now, the next section in the book is pressure difference and buoyant force in accelerating fluids. We have already seen this. Tan theta is A naught by G and all of this stuff you see. So see what he's writing, P1 minus P2. If there is an accelerating thing, right? Suppose there is a figure 13.9, right? The whole elevator is going up with A naught, right?
Yeah.
Now he's saying consider the motion of the liquid contained within this small cylinder A to B. Let P1 be the pressure at A and P2 be the pressure at B. Forces acting on the liquid contained in the cylinder in the vertical direction are P1 delta S, so downward direction is P2 delta S. Weight is downward. Weight is downward is mg, which is delta S into Z into rho G. Z is the height, I think, of the whole column, right?
Yeah.
Correct. So what is Z? See where the Z variable was introduced. Vertical height. He's saying let A and B be 2 points in the liquid, B being at a vertical height Z above A.
Yeah.
So he's balancing all the three forces, but actually it is not balanced because the whole column is going up at A naught, right? You are getting P1 delta S minus P2 delta S minus mg is equal to m A naught, right?
Yeah.
So P1 minus P2 delta S is mg plus A naught and m is delta S Z rho G, right?
Yeah.
Okay. So delta S Z rho is m, not G, because G plus A naught came already. So what we are getting is P1 minus P2 is rho G plus A naught into Z, right?
Yeah.
Yeah.
So basically, in any situation, change in pressure is equal to rho of the liquid G effective into height,
Height. Yeah.
right? And here G effective is G plus A naught because you're going up with acceleration A naught.
A naught.
If you are going down with acceleration A naught, you would have G effective is G minus A naught,
Minus.
Yeah. Yeah.
right?
Yeah.
So that is the situation. So in case the elevator was freely following, the change in pressure would have been zero because G
Zero.
effective would have been zero,
Zero.
Right.
Yeah.
Yeah.
correct? So that is simple enough. The next couple of sections we have already discussed, not very difficult. You can read it. Now we come to the more interesting parts, which is fluid flow. Okay. So fluid flow basically is very complicated actually. Uh, Fluid flow is something that is still unsolved. Like people have not figured out a way to solve fluid flow and predict where the fluid will be at any time, point in time, because it is a very chaotic system. Like
Right.
what will happen to a particular particle is completely dependent on what is happening to neighboring particles, right?
Yeah.
And it is hard to keep track of all of it. Like in higher physics, you will learn something about the Navier-Stokes equation, which is an equation for fluid flow. However, this Navier-Stokes equation has also not been fully solved and it's unsolved right now. Like the implications of this are unsolved. So right now we don't know exactly what happens. We can sort of guess, and under very strict assumptions, we can predict what will happen. So what we'll be studying is the type of flow called steady flow of fluids. So steady flow versus turbulent flow. Turbulent means a lot of chaos here and randomness.
Yeah.
So steady versus turbulent flow. So he's describing what is steady flow and what is turbulent flow. So he's saying as a particle, okay, consider a liquid passing through a glass tube, figure 13.11, right?
Yeah.
Concentrate on a particular particle A, particular point A in the tube, and look at the particles arriving at A, right?
Yeah.
If the velocity of the liquid is small, all the particles which come to A will have same speed and will move in the same direction. So basically what he's saying is if you focus on A, you will notice that under certain conditions of small speed and all, you'll find all particles that arrive at A will again go in the same direction and also with the same speed.
Yeah.
Yeah.
As a particle goes from A to another point B, its speed and direction may change, but all the particles reaching A will have the same speed at A, and all the particles reaching B will have the same speed at B, right?
Right. Yeah.
Also, if one particle passing through A has gone through B, then all the particles passing through A will also go through B.
Yeah.
Like flow is completely predictable as long as you know or you focus on any particular point in the flow, you will realize that everything that happened, so at that moment, whatever is the velocity of the particle at that point will be the same forever. Like it doesn't change. Like
Yeah.
new future particles will come and they will arrive there at the same velocity and they will go from there in the same direction. Correct?
Yeah.
Yeah. Yeah.
So it is very predictable in that sense. So this doesn't happen all the time. Very rarely you will see perfect steady flow, but it can happen in certain situations, and we can analyze steady flow situations to solve it and get some answers. We cannot
Yeah.
analyze turbulent flow where things change. Okay. In turbulent flow, what will happen is right now a particle is coming at some point with 10 meter per second, and later after 1 minute it might be at 12 meter per second, right?
Yeah.
That is a turbulent flow, or going in a different direction. That is
Yeah.
turbulent, right? So in steady flow, the velocity of fluid particles reaching a particular point is the same at all time, right?
Yeah.
Yeah.
As
Yeah.
each particle follows the same path as that taken by a previous particle passing through that point, right?
Yeah. Yeah.
So this is streamline flow. This is also a name for steady flow is streamline flow. Okay. Now line of flow or streamline. The path taken by a particle in a flowing fluid is called the line of flow. The tangent at any point on the line of flow gives the direction of motion of the particle at that point, right? So line of flow could be a curve, and the tangent tells you which direction particles are going on that, right?
Yeah, yeah.
Mm-hmm.
So in case of steady flow, all the particles passing through a given point follow the same path, and hence we have a unique line of flow passing through a particular point, right?
Yeah, yeah.
Like
Yeah,
you will
yeah,
be able to draw a line of all particles that will cross a particular point and then go to some other point, right?
yeah, yeah.
However, in turbulent flow, the line will break. No? It will
Yeah,
go
that will
the
be.
next instant. It will be totally different, right?
Mm-hmm.
Yeah,
Correct. So, thus the tangent to the streamline at any point gives the direction of all the particles passing through that point. It is clear that two streamlines cannot intersect.
hmm.
Otherwise, the particles reaching at the intersection will have two different directions of motion, right?
Yeah,
Yeah,
yeah.
yeah,
So two streamlines will not intersect. They will just keep flowing in a particular way because otherwise it is confusing for the particle, right? So next one is tube of flow. Tube of flow is basically an area or a collection of lines of flow, right?
yeah.
So many streamlines can enclose a cross section, and that cross section is called a tube of flow.
Tube.
Again, this is also a steady flow situation only, right?
Yeah, yeah,
When a liquid is passed slowly through a pipe, the pipe itself is one tube of flow, right?
Yeah, yeah.
Then
yeah,
another term is irrotational flow of an incompressible and non-viscous fluid. Okay, so what we are
yeah,
studying here is these terms you need to know about. So irrotational flow means flow is not there are no circles in that flow. Okay, like it is
yeah,
not swirling; it is going in a streamline, right? So
Yeah,
sometimes
yeah.
you could get a
yeah,
situation if you see water sinks in a basin and it goes around and round, right?
Mm-hmm.
Correct.
yeah, yeah, yeah.
So that is a sort of a vortex formation, and that is called swirling flow, which is a rotational flow, right?
Yeah, yeah,
Irrotational means it is not that; it is streamlined, straight flow, right? Then incompressibility means that the density of the fluid at is the same at all points and remains constant as time passes. So in general, that is the case when steady flow is happening. The
hmm.
particles are passing through, right? So at any given point of time in a given cross section of the fluid, same number of particles will be there because some will be
Hmm,
entering,
hmm,
some
hmm.
will be leaving. And it
Yeah,
cannot
yeah,
be that
hmm.
fluid is accumulating at some point. That is not
Yeah.
the case. Okay, so incompressible fluid means its density is uniform and it remains constant in time,
Constant.
right? It doesn't change the density, right?
Mm-hmm.
So
Yeah.
this assumption is quite good for liquids and is valid in certain cases of flow of gases. So assumption is almost always true for liquids. Like liquids are not compressible very easily. Okay, and some gases is not true always, but in some cases it will be true.
Yeah, hmm.
Yeah, yeah.
Viscosity. What is viscosity? Viscosity is the internal friction in a fluid. So when one layer of the fluid is passing over a lower layer, there is a friction between the two layers as the fluid passes over, right? So that friction is called viscosity. So whenever there is some viscous fluid, then it will be hard to go through or hard for a particle to travel through that fluid because it will face this internal friction always, right?
Yeah, yeah.
Some fluids are more viscous than others. Okay, so
Okay, yeah.
okay, he's explaining irrotational fluid flow means there is no net angular velocity of fluid particles. Okay, that we have already discussed. So now, once we know about these restrictions, so what are the restrictions that we are talking about? We are talking about steady flow. We are talking about irrotational flow, right?
Yeah.
Yeah,
And
hmm.
non-viscous fluid, and also incompressible, right? So if
Mm-hmm.
we are talking about incompressible fluids, non-viscous fluids, irrotational and steady flow, right? In
Yeah,
those
hmm.
conditions, now you have two predictions. One is a equation of continuity, right? Equation of continuity.
Continuous.
Continuity equation is a statement of conservation of mass. Conservation of mass. Why? Because what it says is uh, area into velocity a1 v1 will be equal to a2 v2 for any two cross sections. Suppose there is a fluid like this flowing through a pipe, right? Correct.
Yeah.
And fluid is flowing like this. And suppose this is a situation where these conditions are satisfied, okay? Then fluid is incompressible, no? So it cannot be compressed. So density
Yeah.
of fluid cannot increase suddenly. So what happens is when the fluid comes out, it should come out with a higher velocity, right? V2 is higher than this V1. Why? Because area A1 is higher than A2, right?
Yeah. Yeah.
A1 V1 has units of meter cube per second, right?
Hmm.
A1 V1 units are basically volume per second.
Second, yeah.
So basically, what is the volume per second of the fluid that enters this column? So that should be equal to the volume per second that exits the column, no?
Yeah. Yeah.
If that was not true, you would have compressible fluid, right?
Right.
The
Yeah.
density of the fluid will have changed then, right?
Yeah. Yeah.
Yeah,
Because
yeah,
more fluid would have been inside or less fluid would have been inside, right?
Hmm.
So under the assumptions of incompressible fluids and all, if the fluids are moving in a steady way, then you always have equation of continuity, which is saying that the mass of fluid that enters is equal to the mass of fluid that leaves, right?
Yeah.
Okay. So that is equation of continuity. Equation of the Bernoulli's theorem is a statement of conservation of energy. Bernoulli's theorem is a conservation of energy statement. And how do we derive Bernoulli's theorem? So that is very important to know how to derive it. So he gives a nice example here. He takes two columns like this, one column like this, and it takes a portion of the fluid here and a portion of the fluid here. Okay.
Yeah.
Now after some time, so basically he's saying, oh, not a portion of the fluid is like this. AB is a portion, and then A dash B dash is the after some time location. Okay. So
Yeah.
the entire fluid was in A to B, and we are thinking about the A to B region of the fluid, right? After some time,
yeah,
A goes to A dash and B goes to B dash, right?
Yeah. Yeah.
So think about it. Forces here. Let's write it down properly. This is P1 A1, right? Pressure 1 A1, correct?
Hmm.
And this is pressure 2 A2, correct?
Yeah.
Let's say this column was at a height of H1 from the baseline, and this was at a height of H2 from the baseline, right?
Yeah. Yeah.
So applying, there are only two forces, this force and this force, correct?
Hmm.
I mean, there are forces from the walls, but the wall forces are perpendicular to the motion, right? So
Yeah.
what I'll do is work energy theorem. Work done by pressure plus work done by gravity should be equal to change in kinetic energy, right?
Hmm. Yeah.
Correct. So change in kinetic energy of the body would be the kinetic energy final minus kinetic energy initial, right?
Yeah.
Now, you have to be careful about all of these works and all. Okay. So work done by pressure, let's say, work done by pressure would be P1 A1 into this distance, right?
Yeah. Yeah.
Correct. So this distance will be whatever is the velocity of the fluid here, V1 into delta T, right?
Right. Yeah.
Let's say velocity of the fluid was V1 here. So V1 into delta T in time T, right? That is the distance. Correct?
Yeah.
So work done would be P1 A1 V1 delta T. Work done by pressure here. Work done by pressure here would be negative, no? Because it is moving in this side, right? And its speed is V2, so distance is V2 delta T.
Right. Yeah.
So work done will be
um,
minus P2 A2 V2 delta T, right?
Hmm. Hmm.
Work done by pressure here. So the difference will be P1 A1 V1 delta T minus P2 A2 V2 delta T, right? That will be the total work done by pressure,
Yeah. Yeah.
right? Then we have work done by gravity. Work done by gravity is U initial minus U final, right?
Yeah.
minus del U. So U initial minus U final you have to calculate. So he does a nice thing here. He is thinking about this A to B portion, and he's saying A to B portion potential energy is my U initial, right?
Mm-hmm.
So this A to B portion potential energy will be made up of potential energy of this portion and potential energy of this portion, right?
Yeah.
A dash B and A to A dash, right?
Yeah. Yeah.
Yeah. Yeah.
So U A dash B plus U A dash minus final potential energy is minus U A dash B minus U B B dash.
So 1 second, can you just explain this part, the potential energy one?
Final potential energy is potential energy of A dash B dash, no?
A dash. Yeah. Yeah.
Yeah.
And initial potential energy is potential energy of AB, right?
Right.
Yeah.
Yeah.
So potential energy of AB portion is composed of potential energy of A dash B portion plus A dash portion.
A dash.
Yeah.
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 And potential energy of A dash B dash is potential energy of A dash B again and B B
B B
dash.
dash.
Right.
Yeah.
Yeah. Okay. Got it. Yeah.
So A dash B and A dash B cancel, right?
Yeah.
Yeah. Yeah.
You'll get A dash minus B B dash potentials, right?
Yeah.
So mass in this much portion into height h1 here, and that's it, ngh, right? And minus ngh here, right?
Yeah.
So mass in this portion will be rho into what is the area of this portion? Let's say it is a1, right? It was a1. Rho a1 into s1, this distance, right? Which is v1 delta t.
Yeah.
This is the mass in this portion, no?
Yeah. Yeah.
Mass into g into h1, right?
Yeah. Yeah.
Correct? Minus
Mm-hmm.
mass in this portion will be rho a2 v2 delta t into g into h2, right?
Yeah.
Correct?
Yeah.
So we have this difference, this minus this plus this minus this, right?
Hmm.
That should be equal to change in kinetic energy, right?
Yeah. Yeah.
Yeah. Yeah.
And again, kinetic energy do the same thing. Kinetic energy final is kinetic energy of a dash b dash, right? So
Mm-hmm.
that will be composed of kinetic energy of a dash b plus b b dash.
B B dash.
And again, subtract kinetic energy initial, which will cancel the a dash b portion initial, right?
Yeah. Yeah.
So it will
Yeah.
be kinetic energy of b b dash minus kinetic energy of a dash, right?
Yeah.
Correct.
Yeah.
So
Yeah.
when you do that calculation, again, you have to write the mass correctly. Half into m of b b dash into b b dash velocity is v2 square minus half into m of a dash into v1 square.
Yeah. Yeah.
B b dash mass would be rho into a2 into v2 delta t, right?
Yeah.
Rho a2 v2 delta t, right?
Yeah.
Because a2 into v2 delta t is this much volume,
Yeah. Yeah.
and that is the total mass then. And this mass is rho into a1 into v1 delta t,
Yeah.
Mm-hmm.
right? So you'll get everything will come in terms of this a1, a2, v2 delta t, and so on, right?
Yeah.
So now total work done he is doing, work done by what is w1, w2, w3, what the same things that we saw, right? W1 is this,
Yeah.
W2 is this, and W3 is calling this.
Yeah.
Mm-hmm.
So he took all this is equal to change in kinetic energy would be this expression putting the mass values, right?
Yeah. Yeah.
So you can see the explanation there. Kinetic energy is again he's doing half delta m v2 square minus half delta m v1 square, right?
Yeah.
Yeah.
Now he will simplify this now, equate them and simplify it a little bit. And he also knows that a1 v1 is equal to a2 v2, by the way, because equation
Yeah.
of continuity, right?
Yeah.
Yeah.
A1 v1 is equal to a2 v2 is also true, and this work energy theorem is also true. Now if you read this a little bit, you will realize that this equation is coming, the 13.10 is coming.
Yeah.
See, somewhere he will use a1 v1 is equal to a2 v2. See, earlier in part where he is writing 1, right? The mass of the volume of liquid is del m is equal to rho a1 v1 delta t is equal to rho a2 v2 delta t, right?
Yeah, yeah, yeah.
So that del m he will use everywhere. So when he wrote work one he simplified by writing del m by rho,
Yeah.
right? A1 v1 delta t is equal to del m by rho, no?
Yeah.
Mm-hmm.
Yeah.
Yeah.
Del m by rho, right?
Yeah.
Everywhere
Yeah.
he is putting del m initially only, so that his final equation is not looking that complicated
Yeah.
when he puts work energy theorem in.
Mm-hmm.
So once he does that, he gets the condition that rho 1 plus rho g h1 plus half rho v2 square v1 square is equal to rho 2 p2 plus rho g h2 plus half rho v2 square, right?
Yeah, yeah.
This is called Bernoulli's equation. Basically what we get is Bernoulli's equation says that rho plus p plus rho gh plus half rho v square is constant. So this is a statement of work energy theorem only, conservation of energy. Okay.
Yeah.
So now this he will utilize at many places for deriving all of these results. Okay. So applications of Bernoulli, the next section, let's see. He's saying hydrostatics. So he's saying if the speed of the fluid is zero everywhere, right? We get the situation of hydrostatics, right?
Yeah.
If you put two different points, and v1 and v2 are zero, then you get rho 1 plus rho g h1 should be equal to rho 2 p2 plus rho g h2.
Right. Yeah, yeah.
So that is the equation that is expected. Pressure difference is equal to rho g h2 minus h1, right?
Yeah.
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 Then look at the speed of efflux thing. So he's saying, consider a liquid of density rho filled in a tank of large cross-section area, right? There is a hole in the whole of cross-sectional area A2 at the bottom of the liquid, right? At the bottom.
Yeah.
Liquid
Yeah,
is
yeah.
flowing out through the hole, right? The
Yeah.
situation is shown in that figure. Suppose A1 is much bigger than A2, right? And he's saying let V1 and V2 be the speed of the liquid at A1 and A2, right?
Mm-hmm.
Now, this point is very important. He's saying as both the cross sections are open to the atmosphere, the pressures there are equal to atmospheric pressure, right?
Yeah.
Yeah, yeah.
Pressure at A1 and pressure at A2 will all be atmospheric pressure because both are open to the atmosphere.
Yeah.
Yeah.
So the height of the free surface above the hole is h. Let's say the height difference between them is h, right? So he's
Mm-hmm.
taking the baseline at A2, right?
Yeah.
So he's saying P naught plus half rho V1 square, which is A1's point, plus rho GH should be equal to P naught plus half rho V2 square, right? Plus
Yeah.
rho G into 0, right?
Zero. Yeah.
So by equation of continuity, you also have A1 V1 is equal to A2 V2, right? So V1 can be written in terms of V2 like A1 A2 V2 by A1, right?
Yeah. Yeah.
Mm-hmm.
So instead of V1 in the first equation, he has put A2
V2.
V2 by A1, right?
Yeah.
Right. Yeah, yeah.
And he gets this equation. This equation tells you V2 in terms of all of the other variables, right?
Mm-hmm.
Ah.
So he has solved for V2 and he's getting this relation 1 minus A2 by A1 whole square into V2 square is 2GH, right?
Yeah.
In case A2 by A1 is too small, right, and can be ignored, if it is too small and can be ignored, then equation becomes V2 square is equal to 2GH, right?
Yeah.
And V2 is equal to root 2GH,
Yeah. Yeah.
which is the same as almost saying water is falling through a liquid, right? Freely
Yeah.
falling, correct?
Yeah. Yeah.
The speed of liquid coming out through a hole at a depth h below the free surface is the same as that of a particle fallen freely through a height h under gravity, right?
Yeah.
Mm-hmm.
Yeah.
So in this case, you're getting almost like root 2GH, which is almost as if a particle was falling through gravity, right?
Yeah.
Yeah,
Yeah.
yeah.
Correct.
We can find V1 also, right? The same way.
Huh? V2
Yeah.
once you can get V1, whatever you want, you can get basically.
Yeah, yeah.
Huh. Okay. So that is speed of efflux. So again, now Venturi tube is very simple and very useful also. So what he's doing is he's taking a horizontal column this time, and 2 points he's calculating Bernoulli's theorem he's writing, right? Those 2 points in the fluid are at the same level. Okay. So one is that first point P1, and the second is the other point P2, right?
Yeah.
So he's writing P1 plus half rho V1 square is equal to P2 plus half rho V2 square, right?
Yeah, yeah.
And P1 minus P2 is equal to half rho V2 square minus V1 square,
V1 square.
Yeah.
right? Now what he is measuring is by the height of a fluid column, he will measure the actual pressure difference between P1 and P2. Because he can put a fluid column above and say that P1 should be equal to rho g H1 and P2 should be equal to rho g H2, right?
Yeah.
Right? So if you know these two things, right? Rho g H2 minus H1 will be equal to half rho P2 square minus V1 square, no?
V1 square, yeah.
So now you will be able to know the velocity of fluid inside the tube just by measuring the height of that column, right?
Yeah, yeah.
See, velocity of fluid inside the tube is hard to measure, no?
Yeah. Yeah.
Right?
Right, yeah.
How will you know how fast the fluid is going inside a tube? So this is a way in which externally, by measuring height of fluid column outside, you can say the velocity of fluid inside, right?
Yeah, yeah.
So that is quite useful. Then you can read the aspirator pump and all of this. Not very difficult, I'm assuming. Change of plane of motion of a spinning ball is quite interesting. So he's saying quite often when swing bowlers deliver the ball changes its plane of motion in air, right? Such a deflection is called is explained on the basis of Bernoulli's theorem. So swing that happens, so there is a shiny side and there is a rough side to the ball, right?
Right.
So shiny side allows flow of fluid or flow of air to happen very fast, right?
Yeah.
Yeah.
And
Yeah.
rough side will have some lesser speed of air flowing, right?
Yeah.
Right.
So
Yeah.
now there is a clear difference between V1 and V2 on two sides of the ball, right?
Yeah.
So there will be similar P1 minus P2 is half rho V2 square minus V1 square, no?
Yeah. Yeah.
Yeah.
So there will be a pressure difference between two ends of the ball, no?
Yeah.
Right. Yeah.
Yeah.
Just by the previous section's equation, okay?
Yeah.
Velocity of air is different at two different surfaces of the ball, then pressure is also different at those 2 points.
Different. Yeah.
Yeah. Yeah.
So if pressure is different, then there will be a net force on the ball in some direction horizontal, no?
Yeah.
So when the swing bowler is delivering the ball, he's keeping one side shiny, one side rough, right?
Yeah.
So,
Yeah.
so shiny side will have higher velocity of fluid, right?
Yeah.
Right.
Or
Yeah.
air, and rough side will have lower velocity.
Sure, yeah.
Then what will happen? P1, the shiny side will have higher pressure, and the rough side will have lesser pressure, right?
Yeah.
Yeah.
So ball will swing towards the
Towards
rough
the
side,
rough side,
so away from the shiny side, right? So then
Yeah.
he will
Yeah.
flip the ball and it will go the other way, right?
yeah.
So this is Bernoulli's theorem only, and that is explained by this. Now what you can do is go through the examples, go through the exercise. You should attempt the last 5-10 questions at least of this chapter, because they are nice and interesting. Also the Archimedes questions that are there here, flotation questions, they
Yeah.
are also interesting. So there are only 5 questions, so you can attempt as many as you can, right?
Yeah.
Yeah. Practice some questions. We'll have a class on sound as well as this problems.
Yeah.
Okay. Yeah.
Okay. We'll try to do a class tomorrow. I'll let you know. Okay.
Sir, is Thursday possible because tomorrow we actually have a test.
When?
In the evening.
Test is what? Mains or advanced?
Mains only.
What is the syllabus?
Full portions.
11.
Yeah.
Okay. Okay, then we'll do it on Thursday then.
Okay. Yeah.
Okay. Okay, no problem. I'll see you then.
Yeah.
Okay. Bye, sir.
That's
Bye.